Welcome, everyone. We just heard an excellent talk by Vicki, who is visiting us from McGill, and she will speak in a few minutes. She spoke about pulsars, FRBs. We learned quite a bit, but there is even more exciting stuff to come. Actually, I should mention that today we have 4 presentations, all by women, and in terms of next time, we'll try to exercise affirmative action to allow some men to speak, but this is an unusual lunch today. The first speaker is Anastasia Fialkov, who is a newly appointed ITC postdoc. She came to us from Paris, and before that, Tel Aviv. And she will talk about probing the early universe to the 21-centimeter line of hydrogen. And then we'll hear from Vicki about Magnetar puzzles, which would be exciting for us to try and solve. And then after that, we'll hear from Kate Alexander, who is a graduate student in our department working with Guido Berger, who made a discovery of an outflow based on radio observations of a tidal destruction event. Which the paper, as far as I understand from Astronomical, was submitted to Nature based on the style. But
I can't really.
You cannot tell us. And then finally, we'll hear from Sherry Ye, who is visiting us from the National Astronomical Observatory of Japan, and she will talk about mid-infrared imaging of very young and massive clusters near galactic nuclei. Anastasia.
Thank you, Ari, for introduction. It's a pleasure to be here and tell you all what I'm doing. And I hope to collaborate with at least some of you. So please feel free to talk to me after you know what I'm actually doing. So I will tell you about 21-centimeter signal from high redshifts and how can we learn about the early sources of heat based on this line. So this is a cartoon version of the history of the universe that we know. Out of this, we probed CMB with a great precision, and it's a 2-dimensional surface at redshifts around 1000. And we also know quite a bit about our home universe, galaxies, large-scale structure, planet formation, and so on. So it's this bit of the picture. However, all the majority of it, which includes dark ages when fluctuations in matter density grew linearly, formation of first sources of heat, light, and UV radiation, and finally reionization when the sources heated and reionized all the intergalactic medium. We haven't really probed anything out of it, and we have only a schematic understanding of what happens during all this history. This environment can be very different from what we observe today. In particular, we believe that intergalactic medium here was cold and neutral and mainly composed of neutral hydrogen, which composed 74% by mass of the intergalactic medium. The dark matter halos were very small, and star formation first started in very rare regions of the sky where density was high enough. There were also supersonic flows between dark matter and baryons predicted to exist on the baryon acoustic oscillation scales of 100 megaparsecs, which provided bias to star formation. And populations that existed at high redshifts were most likely different from what we observe today. In particular, black holes were small and grew slowly, and eventually some of them grew into the supermassive black holes that we observe today. First stars were most likely very heavy, up to 1,000 solar masses, and they were metal poor. Their destinies were different from what we see today. For example, some of them could have exploded as spare instability supernovae. And also, X-ray sources could have been different from what we see today. In addition, some feedbacks, which we don't see today, could have been active at high redshifts. So one the future is actually bright, since there are chances that we will observe this epoch with a 21 centimeter signal of neutral hydrogen, and there is a lot of observational effort going on worldwide. There are telescopes which are already active, and also plans to build, for example, Hera and Square Kilometer Array, which have very good chances to probe high redshift universe and tell us a lot what happened at them. So the holy grail for these telescopes is the 21 centimeter signal of neutral hydrogen. It's just a spin flip transition of neutral hydrogen atom. This transition is forbidden and happens only once per 100 million years for each atom. But luckily for us, there are a lot of these atoms in the early universe which was most neutral. And overall, the intensity of this radiation is predicted to be strong enough to be observed with these radio telescopes. So this radiation provides 3D information about the universe. Since it's a line, every neutral hydrogen cloud which is located at particular redshift emits or absorbs this line to or from the CMB. And we can today measure this information as a function of the redshift at wavelength. So from each redshift, we have independent snapshot. So compared to the CMB, which is just two-dimensional surface, we would have a three-dimensional picture of the universe. And this signal probes the neutral hydrogen throughout this epoch. So we would be able to constrain epoch of ionization, cosmic dawn when first sources formed, and eventually even dark ages. So my job is actually to predict and model this signal. And the most interesting phenomena here is that this signal depends both on small scales on which sources form and emit radiation, and on large scales on which there are fluctuations in velocity and density fields. So to correctly predict observables which the telescopes will measure, we need to both include very small scales and very large scales. And we need to have enough flexibility to probe parameters of the high redshift universe which we have no idea, or which we have only a vague idea about. So I use semi-numerical methods using subgrid models to input star formation, and I do simulations with resolution of 3 megaparsecs, but of large cosmic volumes to correctly predict the fluctuations in this signal. So the expected signal looks like this. This is a monopole, so it has a function of is a function of redshift of frequency, and it's just at every redshift we just average over the sky, and we have information how the global signal varies with redshift. And we can also look on the fluctuations of the signal as a function of redshift at particular scale. So both the global signal and the fluctuations have information about what happened at each stage of the evolution of the universe. I will focus on this peak in the spectra, which is imprinted by X-ray sources, non-homogeneous distribution of X-ray sources, and it actually depends on the character and spectral energy distribution of the high redshift X-ray sources. So there is a variety of theories that predict that high redshift X-ray sources can be X-ray binaries, or just thermal emission from hot gas and galaxies, mini quasars and small black holes, or even dark matter annihilation, cosmic rays, and magnetic fields. So we don't have a good idea what really happened, and the 21 centimeter signal, as I will show you in the last 2 minutes, I guess, provides a very powerful probe of these sources. So I will consider two types of sources, sources with a soft spectral energy distribution, which input most of their energy close to themselves, because these photons mainly have a small mean free path, and sources with hard spectrum, whose photons travel long distances before they can get absorbed by the gas and hit the intergalactic medium. So even if these two types of sources have the same luminosity, the effect on the surrounding is quite different. Soft cell sources are more efficient in heating up the universe, and they imprint fluctuations on small scales in the temperature of IgM, whereas hard sources have their radiation gets redshifted on the way to the hydrogen, which gets heated by the photons, and therefore less energy is eventually inputted in the IgM, and the fluctuations on small scales are erased due to the large mean free path. So a cartoonish version of what happens to this peak in the power spectrum of 21 centimeter imprinted by X-ray photons is this. I consider two types of spectral energy distribution. So soft is the standard power law used often by modelers when they predict 21 centimeter signal. And the hard X-rays, this is a realistic spectrum from a population synthesis simulation of X-ray binaries at high redshifts, done here by Tassos Fragos, who was an ITC fellow, I believe. So when we consider the soft X-rays, we clearly see the peak imprinted in the power of 21 centimeter signal on particular scales, whereas for hard X-rays, this peak is erased, and we will see only lambda alpha peak imprinted at high redshifts, and there is no information from heating on this scale. So when we follow the evolution as a function of wavelengths, here I show plots for different wavelengths, we see that we can distinguish between soft and hard X-rays, judging by the presence or absence of the heating peak from this power spectrum. So again, this is power spectrum as a function of redshift, and let's focus on this blue line, which is 0.1 inverse megaparsecs. On your I'm not German, so I can take a couple of minutes. So the blue line here on the right-hand side for the soft spectrum does have the heating peak, as you see here, while in the case of hard spectrum, we don't see this peak at all. So measuring or not this peak on particular scales can just constrain the mean free path. And the hardness of X-ray sources also has an impact on reionization, as we showed recently. So for hard X-rays, as I mentioned, the universe is colder because they're less efficient in heating up the gas, and also fluctuations are suppressed. So at the same redshift, we see a totally different picture from hard X-rays and soft X-rays. In the case of soft X-rays, the gas is hotter, there are stronger fluctuations, and we see it also in the brightness temperature of 21 centimeter signal. Okay, I will jump over this and go to conclusions. So I hope I convinced you that the future in radio is very bright, and it provides a powerful probe to constrain high redshift astrophysics, in particular nature of heating sources. And that's it. I'll stop here, and thank you for your attention. Lucky me.
So when you take into account the foregrounds and the observations, how much the volume of the universe do you need to see the peaks of the power spectrum?
So I'm a theoretician. I don't really take foregrounds into account.
If you are going to need 10 universes,
well,
this is not very interesting.
Right. No, for sure, SKA will be able to probe it, and it will have enough sensitivity.
Sorry? Can you give me a better feeling about how much you need to see the peaks on the power spectrum of X21?
How much you need to see?
How much to see those peaks in the power spectrum of the 21 centimeters? How much volume do you need of the universe?
You need to cover tens of square degrees at least in order to get a reasonable signal to noise. But the point is, it's not just a question of which fraction of the sky you're covering, but also how big.
Exactly, the volume, right?
Right. And the main concern is not so much in the statistics, but it's in the foreground.
No, it's the next generation. It will be feasible.
Right now, people are struggling with the programs, and of course, the frontier is with Terra. That is what people are working on. It's quite likely that this will be the first instrument to detect this. More questions? Like everything was clear. And Anastasia will be around, so.
Yes, please feel free to stop by.
Okay, so I was told to speak about something different from what I spoke about earlier. I'm going to talk about magnetars. And this will actually have an interesting relevance to the previous talk. You might be surprised by that, but you'll see why. So magnetars, these are very volatile neutron stars. We know of 23 confirmed and 28 total possible in our currently. So they're rare neutron stars. They show large X-ray and soft gamma ray bursts. We know that they're young. They typically have ages less than 10 kiloyears. They're found in the galactic plane, and I'll quantify that a little better shortly. They're found in supernova remnants. They show X-ray pulsations both in outburst and in quiescence. And some are seen optically, and some are seen in the radio. The pulse periods that are observed are in the range of 2 to 12 seconds, and all of these objects are spinning down. And the luminosities that we observe in the X-rays and the soft and hard X-rays exceed, in some cases, by many orders of magnitude, the spin-down luminosities, which is problematic for identifying an origin of the emission. Energetically speaking, you might think they're accreting, but there's no evidence for any companions to be accreting from. And so today, the standard model for these objects is that it's emission powered by the decay of an enormous internal magnetic field on the order of 10 to the 14 to 10 to the 15 Gauss. And that's where the term magnetar comes from. It was coined by Rob Duncan and Canadian Chris Thompson. Magnetar radiative activity, it comes in three broad categories. There's giant flares, and those are very rare. We've only observed 3 of them in about 40 years. When the giant flare goes off, it briefly outshines all cosmic X-ray sources combined and can observably affect the Earth's ionosphere when this happens. Then there's the more common outbursts, which involve long-lived flux enhancements by sometimes 1, 2, or 3 orders of magnitude, rapid rise, and then decay over many months. And these are often accompanied by timing anomalies, some sort of glitch in the rotation of the star. And then there's also short timescale bursts, last a few milliseconds to a second, and those are common during those outbursts, but sometimes seen just totally alone. This is the giant flare from 2004 from the Magnetar SGR 1800 plus 06. This was the most intense cosmic transient or solar flare ever observed. And as I said, it had a clear effect on the ionosphere from a source distance of 9 kiloparsecs. So this object really packs a punch. It's one of the few celestial objects can affect our Earth. The total luminosity was about 10 to the 47 ergs per second, and just for fun, in 0.2 seconds, the same energy was released from this magnetar as by the sun in 250,000 years. So magnetars have been discovered, as you can surmise, because of this tremendous dramatic volatility through their bursts, and the Swift BAT and Fermi GBM have been great for finding magnetar bursts. This is a plot of the number of confirmed magnetars as a function of time, and this is when Swift was launched. You can see a sharp upturn in the slope, and this is when Fermi was launched, and again, a sharp upturn in the slope because Those instruments are really good. They designed to find gamma ray bursts. They have a spatially unbiased view of the galaxy, and by that I mean they're sensitive to bursts throughout the whole sky pretty much equally. And by the way, if you're interested in magnetars and you want to know about them, at McGill we have the online Magnetar catalog that's maintained by the Magnetar. Scott will listen. This is a plot looking down on the galaxy at the locations of the known magnetars. The blue dots are actually known radio pulsars. The sun is here, galactic center is over here. And this is, the positions aren't that well known, but the main thing I wanted to show you in this plot is the fact that there's quite a few magnetars now that are just within 1 or 2 kiloparsecs of the Earth, and that's thanks to these missions that have been discovering them. And that brings me, I call my talk Magnetar Puzzles, and these are, I just thought here with so many wonderful people, I would share some of my innermost concerns about magnetars, and here's one of them. What happens when one of those nearby magnetars has a giant flare? I mentioned the one at 9 kiloparsecs visibly affected our ionosphere, and that lasted, almost a minute. What if you bring it 10 times closer? That is, I put a little saddy face because I get nervous when I think about that. And I've tried to contact ionospheric experts to ask what would you do if you flooded with soft gamma rays the ionosphere. And I haven't gotten any responses. So I just thought I'd throw that out there as something, if any of you knows the answer, I would love to know it. But once we're talking about magnetar spatial distribution, so that was looking down on the galaxy. The thing that I thought was quite interesting when Scott and I wrote this catalog paper is that if you look at the galactic scale heights of magnetars, they're extremely low. So that fitting, depending on exactly what model for galactic scale height, we find that magnetars are all pretty much located within 20 to 30 parsecs of the galactic plane. And here you can see the distribution, and this is a cumulative fit. What's kind of cute, if your eyes are really good, you notice that the magnetars actually are a little off from the galactic plane, and you might wonder why that is. It turns out, using just the 23 confirmed magnetars, we measure the deviation of the sun from the galactic plane, and the number that we fit out of the plot matches exactly what was in the literature. And I didn't even know about that in advance, so I was pretty amazed. And so the question is what's the significance of this? Why should magnetars have such a low scale height, even compared to radio pulsars, young radio pulsars? The scale height's quite low. I think this suggests that magnetars may come from very massive progenitors, because those objects do not have much time before they, massive O stars, they supernova before they have any time. They're formed in the galactic plane, don't have much time to move away. And so the suggestion that this low scale height indicates that magnetars are formed as a population from the most massive main sequence stars is actually consistent with other facts that have been known about magnetars. For example, that one has been known in the massive star cluster Westerlin 1, which sets a lower limit on at least the mass of that progenitor of that magnetar to about 40 solar masses. And actually, I think this is a point that is quite interesting in relation to the previous talk, because is it the case that massive stars preferentially produce magnetars and not black holes? If so, why? And then if you ask the question, early in the history of the universe, when many stars were quite massive, could it be that they were producing magnetars that were giant flaring all the time? And what impact would that have on the effects that you were talking about? I think this is something interesting. I've actually been talking with my colleague Gil Holder at McGill about this, but I would love to talk to you more about it. Also, looking at magnetars as a population, this is now a histogram of the spin-inferred magnetic field. So we infer magnetic fields on the basis of the periods and period derivatives using standard equations for magnetic dipoles in a vacuum, which are almost certainly not the case, but we believe probably good to a factor of 2 to 3. And certainly this plot would support that claim. This is now showing these are the radio pulsars color-coded according to their age, a distribution of their magnetic fields. And the red objects, those are the ones that have shown magnetar activity. That is, these kind of bursts, outbursts, flares, and so on. This is just a blow up of this region. And so what you can see is that, just from the magnetar activity alone, it selects for the most highly magnetized neutron stars as measured by spin parameters. And so one other interesting question about magnetars that I wonder about, it looks like the radio pulsar population falls off, and then there's this second peak here, albeit tiny. The question is this magnetic field distribution in newly born neutron stars, is it actually a bimodal thing? Or is it just the case that the high magnetic field neutron stars like to burst more? Those are the ones that you notice the most. And so really the distribution of magnetic fields is not bimodal. There's not a special population. But it just falls off slowly, and you just happen to notice all these ones out here that are screaming loudly at you through their soft gamma ray bursts. So I tend to think it's actually the latter, and which then makes you wonder about what about those radio pulsars that sit, at this part of the distribution. 2 minutes. I see that you're allowed that, so I'm going to do that too. This is the standard p dot diagram, and the radio pulsars are all shown with the same color coding, and the magnetars sit way over here at the very high magnetic field strength. You can see there's radio pulsars that are in the same region of this p dot diagram as magnetars, and the question is, do those show magnetar-like behavior everywhere? Can you unify? Is it really two distinct populations, radio pulsars and magnetars, or are they just really continuum magnetic field? I think this must be the case. There's some studies that suggest that's true, and it suggests there's other transition objects should exist. That is, you should find high magnetic field radio pulsars sometimes becoming magnetars, and in fact, we did find an object just like that back in 2008. This is an X-ray monitoring campaign with XTE that was looking at a rotation-powered pulsar 1846-0258. We were observing it with XTE because we wanted to measure its breaking index, which is a fundamental breaking parameter interesting for radio pulsars. But to our shock, it exhibited this X-ray outburst and subsequent decay over 6 weeks, punctuated by these very short little magnetar-like bursts. So this rotation-powered pulsar briefly turned into a magnetar for about 6 weeks, showing a whole bunch of bursts. And therefore sort of supports this idea of a transition object. And the last thing I want to show you, I'll just skip that, is the breaking index has recently done something interesting. So we wanted to measure the breaking index because it's a fundamental test of radio pulsar electromagnetics, where in standard theory, the spin frequency derivative should be proportional to the frequency to the nth power, n is the breaking index, and for a dipole, spinning down in vacuum, n equals 3. It's easy to show that you can measure, and using this is 2 lines of algebra, by measuring a second frequency derivative for pulsars, you can measure these breaking indexes. All of these are observable parameters, and n has been measured for the Crab pulsar to be about 2.5. It always seems to be a little bit less than 3. And the last slide I want to show is that what's interesting is, using our XTE data before the magnetar outburst, we had measured the breaking index quite well, 2.65 plus or minus 0.01. But since the magnetar-like outburst, the breaking index of this pulsar, this is unprecedented, has changed. A paper just recently published and featured on the AAS NOVA webpage, the breaking index has changed from 2.65 to 2.19. And so that's the last magnetar puzzle I wanted to leave you with. Why does a magnetar-like outburst cause a pulsar's breaking index to change dramatically with no other apparent changes? After that outburst, this breaking index has been measured over 6 years. The pulsar is back to normal from as far as we can tell, but the breaking index has changed radically, and we don't really understand that. And so I want to leave that to you. Maybe one of you can help us solve that problem. So I don't think I can give you a good answer. I think our knowledge of the magnetar population in our galaxy is quite incomplete because most of them sit there quiescent and you don't detect them until they decide to go into outburst. There are papers in the literature that suggest the birth rate of magnetars is something like 10% of radio pulsars, but I think that's a lower limit because we don't know the magnetar population very well. So it's hard for me to answer your question.
10% would be very high because you're talking about massive, much more massive stars and big solar masses.
That is true. That is true.
Yeah, so when you say that magnetars are young events, which means that it might be associated with supernova remnants. What kind of remnants are associated with pulsars? And from the remnants, can we tell what kind of supernova are they?
Yeah, it's a very interesting question, but I'll just say that people have studied the supernova remnants around magnetars, and they don't find any interesting difference between the remnants around magnetars versus remnants around radio pulsars. As far as we could tell, they're type 2. I mean, there's nothing special about them that would help you out. Yeah, even with new star. Yeah.
So let me answer parcel 1. It will be pretty bad. What is going to happen is if you bring it that close, you're going to produce a lot of nitrogen dioxide, get rid of the ozone, and then we're going to get a lot of UV from the sun. So it's not going to be pleasant to have a magnetar that close. Basically, it's going to affect a lot the atmosphere.
But the question, but how quickly will it recover? It's the ionosphere that's
making
making
it. About between 6 months and a few months for it to recover if it is that close.
Because in the current ones, it doesn't recover that long. But
right, but you bring it that close, right? It's 10 times closer. Right?
Okay, well, so that's actually interesting because
so
if you're right,
go underground for a year. Or
so, Vicki, there's actually literature from the GRB people.
yes,
Not as a nearby GRB too, but I think it's exactly this. Get rid of this UV protecting layer, and then the sun zaps you.
yeah.
And apparently it kills off pretty much all the surface life.
It started with steering Colgate
Yeah,
in
okay.
the 70s,
Right.
using his lessons from atomic explosion.
Exactly, right.
He was talking about gamma ray burst influence. And his
Right. So
paper
I think it'll be very interesting to know the really bright guys. How common are your soft GR bursts?
so the softer than GRBs. That's the difference there.
Yeah, so I don't know what that is, but I think that's the really the correct question. How close should it be to completely eliminate the ozone
I
layer?
can give you the number you need. You need 100 kilojoules per square meter
Okay.
to wipe out that. That will be the number you need to come up with.
But is that for a GRB spectrum or for a soft gamma?
For a soft gamma,
Uh-huh.
the one that you are talking about,
Oh.
they will be pretty bad for the.
Okay, we can continue the discussion because it's not very uplifting.
But we are here.
More risks from space.
I have a nationality from when people do things mañana, right? So I'm the one that is allowed to run over time most.
What can we do against the magnetar?
All right. Well, I'm going to talk about something that does not impact the Earth directly in any way, but is still hopefully pretty cool. I'm going to tell you about our discovery of an outflow from radio observations of the tidal disruption event Assassin 14 LI. This is work I've been doing with my thesis advisor, Ido Berger, here at Harvard. So we've had a basic picture of what happens during a tidal disruption event for several decades, but the details are still very much being filled in by observations. So the general picture is you have a star, it's happily going along its orbit, and then it strays too close to a supermassive black hole. The tidal forces from the black hole rip the star apart, and then you get some of the gas becomes unbound and goes out and interacts in the ISM, and some of it spirals back in and forms an accretion disk and accretes onto the black hole, producing a luminous flare of emission. So that is the part that we can study most clearly. This is a plot that shows exactly what the predicted fallback rate of material onto the black hole is as a function of time for a wide range of tidal disruption event models. These include both total disruptions of the star and partial disruptions where some core of the star remains. What I want everyone to take away from this plot is that for most of the models, the accretion rate onto the black hole will exceed the Eddington rate for at least a short amount of time and for up to a year or so. And this is interesting because if the accretion rate is super Eddington, then we expect there to be outflows. We might expect to see a relativistic jet if the rate is highly super Eddington, or just a wind coming off of the black hole. So most of the tidal disruption events we've observed to date, there's only about 20 or so that are fairly reasonably certain to be tidal disruption events as opposed to some other flare of an AGN or other event. Most of them we've discovered at optical, UV, and X-ray wavelengths, and they do not seem to produce any kind of relativistic outflow. But we have seen two particularly unusual high-energy tidal disruption events, notably Swift J1644 plus 57, which our group followed up, and this other Swift event, 2058 plus 05. These were both originally detected in gamma rays and had relativistic jets that were pointed right at us. So we were able to detect them in the radio as well. These are radio light curves for 1644 plus 57 that our group followed up on it for years. And it's cool when you have a relativistic jet and can get radio emission, because then you can learn all sorts of interesting things about the system. You can learn about the energy of the event, the surrounding density of the black hole before the event happened, etc. But these are very rare events. We think that they only happen about 1% of the time that you have a tidal disruption event. So it would be great if we could measure some kind of a slower outflow from one of these more typical events up here, and we have not seen any direct evidence of that in the radio yet. All of the tidal disruption events in the literature, until what I'm about to tell you, we had followed some of them up in the radio. It was all upper limits. That ruled out these relativistic jets, but not anything slower and non-relativistic. So enter the star of this talk. This is tidal disruption event Assassin 14Li. It was discovered by the All-Sky Automated Survey for Supernovae on November 22nd last year. It's been extensively followed up in X-ray, UV, and optical observations, and both the spectral energy distributions and the light curves and spectra taken of these objects, or this object, all show that it's consistent with previous tidal disruption events that have been seen. It's not consistent with a typical AGN flare or with a typical supernova spectrum. This object is particularly exciting because it's only 90 megaparsecs away, but it's the closest optically discovered tidal disruption event to date, which means we have a chance to get these really beautiful, detailed observations of it that just aren't possible for some of the events that we've seen at higher redshift. So in our group's quest to search optical and UV tidal disruption events for evidence of off-axis jets or other outflows, we started following this object up with a very large array in Socorro, New Mexico. We have observations spanning from last December until just last month. These observations have broad frequency coverage. We observe from 1.4 gigahertz all the way up to 24.5 gigahertz. And we've detected a source, and we have to interpret our detection in the context of two archival radio data points. This source was observed twice as part of two different VLA sky surveys in the 90s. They both detected a source at the nucleus of this galaxy with about 3 millijanskis in brightness. So I'll keep that in mind as I go to the next plot, which shows our observations. So this plot on the left is the total fluxes we've observed in these 6 different epochs of observations. The earliest one is these green points over here in December. And then it sort of shifts, the peak of the emission shifts to lower frequencies as we've been following it. We see a very significant fading at high frequencies. So it's a factor of 7 or 8, which is much more variability than you usually see in the radio for any kind of AGN flare. Based on the fact that we did detect, the nucleus of the galaxy was detected before we ever had this this transient event, we suspect that there's probably an underlying component to the radio emission that's due to whatever pre-existing processes were going on. We don't think the radio emission before this event was due to star formation because the optical spectrum of the galaxy reveals it's very red, very dead, not the level of star formation that is possible is not anywhere near enough to explain the radio emission. So we make a very simple model for an underlying quiescent component to the emission, and then we can subtract that off and we're left with the transient component that we see over here. And so we have this wonderful radio emission. We can fit it with a standard synchrotron model. So for an outflow that's expanding and is being self-absorbed, you expect to see a transition between two power laws. So you have a nu to the 5/2 power law transitioning to a nu to the -1 power law. And the emission is very well fit by this model. We just model each SED independently. And then we get out the frequency at which this happens and the peak flux. And then we assume that the electron and the magnetic fields are in equipartition, which minimizes the energy. And then we follow this sort of very standard synchrotron equipartition model. We can get out an estimate for the size of the emitting region and the energy of the emitting region, and also a bunch of other interesting properties of the outflow, which I summarize here. So this plot from left to right, we are seeing the radius versus time. So again, these are individual fits to each of our epochs of data. And then we have the energy as a function of time, the velocity of the outflow as a function of time, the inferred mass based on the kinetic energy of the outflow as a function of time. And then we also put in the density profile as a function of radius and the magnetic field strength as a function of radius. So I want to draw your attention to a couple of interesting things on this plot. First of all, we considered two different models for the shape of the outflow. We assume the red points are for a spherical outflow, so we just assumed that it is isotropic, and then the blue points are for a conical outflow. So we said, well, what if it's not perfectly spherical? What if it's very slightly beamed? So this is a 10% covering fraction. So I think these are sort of two fairly reasonable extreme cases. So the energy doesn't change very much for either of these two outflows. And if we assume that our model for the quiescent component is correct, the energy stays fairly constant. These dotted lines fit the total flux. So it's fitting these curves in the left plot, whereas the solid lines are these curves in the right plot here. So we get an energy of the outflow that's pretty much constant, and we get a pretty much constant velocity for the outflow. The exact velocity changes a little bit depending on what you assume about the geometry, but it's fairly constant, which means that our outflow is in free expansion. It hasn't decelerated. It hasn't encountered enough mass to start slowing down yet. And we have an outflow mass of about 10 to the -3, 10 to the -4 solar masses. So we'll have to bear that number in mind on the next slide. This is a fun consistency check we did. So we have this estimate for how the radius of our outflow is changing with time. So we can, and the velocity is fairly constant, so we can extrapolate that backwards and determine what time was the outflow launched. So we extrapolate backwards and learn that the outflow was launched around mid-August. One of our co-authors, James, who's a postdoc here, has done an independent modeling based on the X-ray, optical, and UV emission of when the period of super Eddington accretion for this source was. So he predicts that the super Eddington fallback starts in around July, and then it reaches peak accretion sort of in September. So if we think that this outflow is a wind associated with the super Eddington accretion phase, that's very nicely consistent. Another thing that's nicely consistent is he's modeled how much mass you expect to be accreted during this super Eddington phase. So this is, I think it's actually no, this is the non-log version of this plot. But so it's about 0.02 solar masses of material is accreted during the super Eddington phase. Our mass of our outflow is about 10 to the -4, 10 to the -3 solar masses of material. So about 1 to 10%-ish of this total accreted mass, which agrees fairly well with theoretical estimates of what fraction of accreted material would you expect to be blown out in a wind during super Eddington phase. I'm running out of time, so I'll just throw this up here and not talk about it much. This is comparing our density profile to density profiles seen around other supermassive black holes for which we have direct observational evidence of the density. It's both lower and steeper, which is interesting. We can talk about that. And then this is the last thing I wanted to show. This is a plot showing the energy for 3 different tidal disruption events. We have this is Assassin 14 Li, and then the only 2 other TDEs previously detected in the radio, which were these 2 extreme events with relativistic jets. And then for comparison, we have a population of gamma ray bursts from the literature and type 1bc supernovae from the literature. So I want to draw this analogy to the type 1bc supernovae population, where most of the type 1bc supernovae have these slow outflows, and only a very small fraction produce these high energy gamma ray bursts. So we only have a very few TDEs in our sample, and most of the TDEs with properties similarly to Assassin 14 Li have been farther away, so if there was an outflow like this, we wouldn't have been able to see it because it wouldn't have been bright enough. But it's possible that there is sort of an analogous situation going on with these tidal disruption events, where most of the events will be down here in this sort of energy range, and most of them may have these lower energy non-relativistic outflows like the one we see here. And then only a few will be up in this higher energy relativistic regime like these 2 events that we have detected previously. So I'll leave my conclusions up, but the takeaway is we've detected an outflow. It seems to be non-relativistic. This conclusion is robust to our exact model for the quiescent emission, or if you don't believe it's there at all, it's still robust. We get an outflow. These outflows may be ubiquitous among TDEs, and with more sensitive radio surveys coming online soon, we expect to see more of them. Thanks.
One, of course, it's quite surprising that there is no slowdown, because typical, even in the average interstellar medium, you don't have significant slowdown of such a small mass ejecta. But another question is, can you do proper motion? Because it's only 90 megaparsecs away and it's moving at 0.04 c. Can you actually see its motion on the sky?
So we can't resolve the outflow yet. It's not at a large, the angular scale of the outflow is not large enough for us to.
But when would you expect to be able to do that?
Possibly as soon as the next 5 to 10 years. I'd have to do the exact calculation, but it should be, it should definitely be possible with VLBI eventually.
Because my guess is that already now it's more than tens of microarcseconds, like 100 microarcseconds.
It's less than that. It's a few. By now I think it's like 80 microarcseconds in our latest epoch. So
We should be able to do it with VLBI.
well, we'll have to put in a proposal with that for that. But yeah, and then to answer your other question, we do infer this very low density. So if you compute how much mass you would have expected the outflow to sweep up so far, it's only something like 0.1% of the mass in the outflow. So it is surprising, I agree, that we have this very low density, but it is self-consistent, this model that we have, that we see the outflow is not slowing down, and we wouldn't have expected it to based on the density we observe.
So, Kate, it looked like your data start from day 150 or something.
Yeah, so.
What happened? You forgot to look, or this thing wasn't right?
So what happened, it wasn't discovered until day 140 or something because the field was behind the sun. So we have a non-detection from July, and then there's nothing until November. So it's,
Blame the sun.
yes, it's all the sun's fault. So that's the nice thing about radio is you can keep observing even when the sun is up, but of course we had no idea to look there in the radio until November.
Okay, why couldn't this be like 1657, but we're not, obviously not in the central beam?
So that's,
1657 probably has a wind outflow that we never would have seen from the main beam.
yeah, so that's a very good question. So that's, so if you had an outflow that was off axis and then you wouldn't see it until it decelerated and slowed down. But we are seeing this, and it's based on the density, it's unlikely that it could have decelerated to the point where we would be seeing it now.
Any other questions? That's a great discovery, and keep up with the good work.
Okay, can you hear me?
Yes.
All right. So in the next 10 to 15 minutes, I'm going to shift the universe to the imaging department from the spectroscopy department. I'm Sherry, visiting from NAOJ Subaru Telescope department. So I'll be talking about using ground-based mid-infrared facility instrument on Subaru Telescope to do neon 2 imaging to pick up very young and massive star clusters, sometimes known as superstar clusters, near galactic nuclei in face-on spiral galaxies. Personally, I'm very interested in utilizing ground-based mid-infrared instruments because they provide superb angular resolution, which I'll show very quickly. And there are many interesting things we can do with that resolution. So young massive star clusters, or superstar clusters, are fairly compact, angular size or physical size about only a few parsecs, half-light radius. They're relatively very young and very massive. So a lot of them have been found in energetic environments, say in merging galaxies and in starburst galaxies. However, they also turn out to be common in normal spiral galaxies as well. And some questions remains unsolved because we know a lot of star formations don't necessarily occur in bound star clusters. So we're looking at this property so-called star cluster formation efficiency, which is essentially the fraction the stars form as bound clusters. And the empirical cluster formation efficiency found in observations, at least in post-merging galaxies, let me see if this works, yes, is that they found that empirically most star cluster formation efficiency is about 8 to 10%. However, we don't know if this is universal. It seems to be the way that in all the observation results. However, in theoretical predictions, theorists predict that the formation efficiency should depend on your environment, should depend on your galaxy, the host galaxy. So from quiescent galaxies, only a few percent efficiency all the way up to starburst galaxy that can be as high as 70% of this formation efficiency. Another question is, do star cluster mass assembly, is this process universal? So by answering that, we can look at star cluster mass function. So in observations, like in this paper, they look at irregular galaxies and spiral galaxies. In spiral galaxies, most spiral galaxies are supported by rotational movement. Therefore, the shear force should be higher than irregular galaxies. But in this case, they look at many galaxies, many star clusters, and the cluster mass function is indistinguishable. However, in simulations, in numerical simulations, they concluded that the high shear environment should really impede massive star cluster formation. So there's a disagreement again. So my personal interest is let's look at massive star cluster formation and their relation with the galactic environment. So ideally, we want to survey star clusters of all ages, and this is the phase that we're looking at is not very well probed. So now with ALMA coming online, so astronomers start to be able to look into many detailed information coming out from ALMA observation in the radio regime when star clusters just being formed and still very embedded in giant molecular clouds. Also, there are a lot of work is being done in the optical regime to look at star clusters already exposed from their natal molecular clouds. So in this phase, it's about 0 to 5 million years, and we're looking at very, very young star clusters. Also, ideally, we like to survey these superstar clusters in all kinds of different galactic environments. We start with a peculiar, interesting environment, which is near galactic nuclei, because in that area, in those environments, star formation doesn't necessarily follow empirical processes that we understand. So the goal is we want to resolve the star clusters. We need high angular resolution. We also need a tracer that doesn't suffer from extinction. And we also need a tracer that can consistently probe bound clusters and also star formation in the field, albeit associations, that's not necessarily clusters. So how do we do that? It turned out ground-based mid-infrared facility can be really ideal for this. Extinction is almost absent at greater than 10 micron. The angular resolution is diffraction limited, and on Subaru telescope, an 8-meter class telescope, the resolution at 12 micron is 0.4 arcsecond. And so we can detect very compact star cluster, compact sources, but also because it's an imaging observation, we can recover all the extended emission as much as the sensitivity allows, and that's associated with the field star formation. You can argue that radio interferometry can pick up these sources for you. The answer is yes, you can find those compact sources, but you lose information of the extended emission. Also, in the optical regime, you can run into the problem that when you encounter optically thick regime, then spectral indices to figure out whether they're thermal or non-thermal sources, that doesn't necessarily work. But in this case, we use neon 2 at 12 micron. It's a tracer that traces very bright and very massive star formation regions. And if we see anything in neon 2, it's a thermal emission in this wavelength anyway. So I'm going to move on. I don't have a lot of time. I just want to show that how it's quite challenging to do mid-infrared observations from the ground because the sky is very bright. It's 0 magnitude per arcsecond square, and it's the best window from the ground. So our raw data will look like that by employing, but we can get rid of a lot of background by chopping the secondary mirror and nodding the telescope. But I won't go into detail, but you get the idea. So eventually, we get something from that to that. Okay, so in our exploratory project, we look at several face-on spiral galaxies. We do have their radio continuum samples, so we do have candidates, and then we observe those with neon 2 imaging on Subaru telescope. I will move on. I'll quickly show you some preliminary results and preliminary images. So here are the radio compact source candidates. The grayscale is the optical image in the V-band, so you can see there are no counterpart in the radio. And this is IC342. This is our image right here. So you can see, so this is so-called unsharp image, so to bring out sharper feature to highlight the compact sources, which are star clusters. So you can see we detect quite a few star clusters, as well as a lot of extended emission. It's all picked up by neon 2. And to give you a sense of how good our resolution is, sorry, a second, but this is the WISE resolution at 12 micron. So our angular resolution is significantly better than space telescope, current space telescope in the mid-infrared. I'll quickly show you. We look at 6946 as well. Again, a lot of extended emission from neon 2, as well as, in this one, the star clusters are not as as obvious as the other one, but we do have bracket gamma observations from Keck AO observations, so that helped us to identify a few sources. Mayfair 2, again, a few more star clusters, some very extended emission, and that's near radio candidates. And this is 7714. We saw star clusters, extended emission. So overall, our preliminary analysis suggests that the cluster formation efficiency varied about from 12 to 22%. So it's crudely agree with other observational results that suggest a 10% efficiency, and also they look at different environments, look at entire galaxies. And what we're looking at is in these clusters within several hundred parsecs near the galactic nuclei, so presumably that's a very different environment, but we don't see very significant deviation as what the theories have predicted. We also made a cluster mass function, and the power index of this the cluster mass function crudely agree with the H2 region luminosity function of these superstar clusters, taking into account the error bar. They also agree with the cluster mass function slope found in other galaxies, and crudely agree with Eric Guido's paper that look at the clump mass function, a molecular cloud mass function. So this makes us think, is there an environmental effect on massive star cluster formation in different environments? That's something we're very interested in knowing, and we're working on that. Preliminary results suggest maybe not so much, but stay tuned. So I just pop up our summary. We definitely detect around 30 superstar clusters. We check their masses that seem to be consistent. And analysis of cluster formation efficiency and mass function seem to suggest there's no strong environmental dependencies of information compared to other environments. And we do attempt to do spectroscopy follow-up from the ground as well in the 10 and 20 micron band, which is quite challenging in 20 micron. But in those windows, there are emission line diagnostics that we can use to constrain the radiation field strength. Therefore, you can constrain the cluster age and also constrain their H2 densities, therefore to constrain the pressure that these H2 regions and star clusters are experiencing near galactic nuclei. And potentially that has that bears the merit to answer whether these star clusters near galactic nuclei are formed in situ or formed via migration. I'll stop here. I'll also take questions if you have questions about super telescope operation. Thank you.
Eric? So you have, there are superstar clusters, right, which are bound and maybe the progenitors of globular clusters.
Yes.
And then there are young massive clusters which may or may not be bound, may have about the same mass, but they would come apart. Can you tell the difference between these two neon pseudo observations?
I don't think at this age, I don't think we can tell the difference. But hopefully, by looking at the full spectrum at all ages, and if they say the cluster mass function just doesn't change, say from giant molecular cloud clumps in this phase and in the optically visible phase, the mass function doesn't change much, it might tell us a story that they might stay bound and they just stay bound. Yeah.
So if the mass functions are power laws, I noticed lots of indices which hover around 2.
Yes,
but there's
minus
something
2.
very special at minus 2, right? If it is steeper than minus 2,
Mm-hmm.
then
If
the mass doesn't blow, total mass doesn't blow up. If it is shallower than minus 2, then the total mass would blow up unless there's a cutoff mass.
It's equal mass for logarithmic mass.
So that's 2. Yeah. So if it's shallower than 2, then the total mass can blow up unless there's a cutoff. So what determines the cutoff? And
I don't think I know the answer.
The biggest cluster.
I think that will go to the star cluster formation theory, that what's the most massive star cluster you can make out of the giant molecular clouds. And that has a lot to do with the feedback mechanisms that I just was at a conference for. So I don't think I know the answer to the cutoff mass, but I can say if the cluster mass function becomes steeper, if we see this trend over time, say from the youngest to the oldest phase, meaning there may be disruption of the most massive star clusters. They probably all become smaller ones, or they just kind of disappear to get whatever happened to them. But if it's shallower, then for some reason there are more massive star clusters formed later. That would be my very quick interpretation of it. But thanks for the question. I will think about it.
We got our time limit. Let's thank all the speakers.
Thank you.